Hey ChemStars, this is Mrs. Vandalay bringing you the last edition of ChemStar video for this chapter on gases. So sadly, I don't have Levi or Lily as your guest speaker today. They are out signing autographs right now, so you're stuck with me. Anyway, what are we doing today? We are determining the density of a gas, and what we're going to do is that we're going to use the ideal gas law. Remember Pivner from the last one? And we're going to rearrange Pivner into making a density formula, all right? Well, we're going to start with ideal gas, all right, and rearrange sulfur density. Well, don't you think we ought to talk about what density is equal to? Mass over volume. So my goal is to rearrange Pivner so I get mass over volume. That makes sense, all right? So I think volume is pretty obvious that V stands for volume, and it needs to be in the denominator. So I think I have to divide both sides by V. But what about mass? What about mass? Which one of these terms can lead me to mass? I think it isn't too hard. It is the moles. Can't you get moles to become mass? And the answer is yes. Didn't we do that on the last video when I kind of threw in that last problem? It's like, well, if we had 15.9 moles of helium, how many grams is that? Remember, we went to the periodic table with that. So I think moles is what we need to get on top to start with, and then we're going to put volume on the bottom. So let's see what I do. All right. Here, I divided both sides by RT, so now I got moles by itself. And now on here, I divided both sides by volume. So I'm getting pretty close, aren't I? All right, so now I have moles over volume is equal to P over RT. Well, now I need to figure out, okay, what do I do here? Well, I need to go from moles to grams, right? So I'm going to put moles on the bottom, and then I'm going to say what? Grams, periodic table, right? So when I say that, what do I really mean? What is it that I'm looking for on the periodic table? Well, I'm looking for molar mass. I abbreviate molar mass by using MM. It's a whole lot easier to write out than molar mass. And what is molar mass? Isn't that the mass of the element per mole? Yes, it is. So that's my link, all right, to get from moles to grams, all right? So what I'm going to do is I'm going to take what I have right here, and I'm going to multiply moles by molar mass, okay? Now, what would your algebra teacher tell me at this point? If I multiplied the right-hand side by molar mass, what should I do to the left-hand side? Yeah, multiply by molar mass. So what does this do for me? I now take pressure times the molar mass, divide by RT, and what was moles times molar mass? What is moles times molar mass? That's your grams. That's your mass. So this is my formula, all right? So either side, I'll say it again, either side is going to be your density, and that's going to be important, okay? So let's go on. So one side represents STP, standard temperature and pressure, and the other side will represent when you're not at standard temperature and pressure. So what I'm going to do is I'm going to flip-flop these two around, all right? I'm going to say mass is equal to, all right, here we go. And guess what? This side represents at STP, and this side represents not at STP. Now watch what happens right here. Now, back in the first chapter or so of this entire year, okay, way back in August, we learned about density. And we learned about density being an intensive property. And what does intensive mean? Oh, this has been a long time since you heard that word, I'm sure. Intensive means it does not depend on how much stuff you have. All right, so like melting point is intensive. You can have a little bit or a lot and it's still going to melt at 0 degrees. It's called ice. All right. What else would be intensive? Color. All right, you can have a big chunk or a little chunk. It should be the same color. What was extensive? Something like, calories. If I eat a big cookie or a little cookie, the calories are going to change. Mass will change. Volume will change. But density is intensive. So why don't we make our life a little bit easier? And if it does not depend on how much stuff we have, then why don't we make our life easier and we assume we have 1 mole? All right, look what happens if I choose to have 1 mole. Well, what is the mass of 1 mole of substance? Well, what did we just say it was over here? It's the molar mass. So it's a thing I look up on the periodic table. And what if I assume I have 1 mole of gas at STP? What did we just learn on the last video? If I have 1 mole of gas at STP, remember that magic number? It's 22.4. So in other words, density of a gas at STP is simply taking the molar mass you read off the periodic table and you divide it by 22.4. Wow, is it that easy? Yes, it really is. What about not STP? All right, we'll do a problem down below. You take the non-STP pressure times the molar mass divided by R divided by the non-STP temperature. And there you'll find the density at that. Now, you're telling me that density changes with pressure and temperature? And the answer is definitely, all right. Why do hot air balloons rise? Because the temperature goes up and, the pressure is going to change and whatnot, and the density changes and it's going to float, isn't it? All right. Why does warm air rise? Same thing, all right. So gases are going to have different densities at different pressures and different temperatures, okay? So let's start with number 1. Okay, so what's the density of hydrogen gas at STP? Oh, it's at STP. So if I have density is equal to mass over volume at STP, aren't I dealing with the molar mass divided by 22.4? Yeah, I am. All right, so what's the molar mass of H2? Well, what's the molar mass of H? Isn't it 1.01? Hey, yes, it is. So what's that times 2? It is 2.02. Divide that by 22.4, and what do you get? You get 0.090. Look at your units, grams per liter. Now, something to think about as far as densities of gases. They're usually in terms of grams per liter. Now, when we were talking about the density of water, the density of iron, and the density of copper, that was always grams per milliliter. Now it's the grams per a much larger quantity, and this is still a pretty small number. So this is why the earliest balloons were actually made out of hydrogen gas, which is very easy to make. I don't know if you remember one of our first labs when we put magnesium and hydrochloric acid and we collected the gas and I lit that little wooden split and went chirp, chirp, chirp. Remember that? We made hydrogen gas, and it's very easy. And that's how they made those original hot air balloons, is that they used sulfuric acid in a metal, I don't know which one, but use sulfuric acid, and you're still going to produce hydrogen gas. But what happened? Holy cow, early 1900s, the Hindenburg came across the ocean and was trying to land in New Jersey, and it caught on fire. Why? Because hydrogen is extremely flammable. So they quit making hydrogen balloons and hydrogen blimps. All right. And then guess what? They used helium. All right. So what is the density of helium at STP? Well, let's find out. All right. So we know the density equals mass over volume. We know that we're at STP. So we can use the molar mass over 22.4. And what's the molar mass of helium? You don't have to multiply it, but I think you just look it up on the periodic table, and it was that 4.0. We already did it in the last video, didn't we? And now divide it by 22.4, and I got 0.179 grams per liter. So you're talking about twice as dense as hydrogen. Well, guess what? Helium is still much less dense than regular air, which is about 75% nitrogen gas. So if you want to figure out nitrogen gas, it's a little bit over 1 grams per liter. So yeah, why don't we just do that real quick? I'll show you what nitrogen gas is. Okay, so I just quickly put up the density of nitrogen gas at STP. The molar mass of N2 would be 28.02 divided by 22.4, and it's 1.25. So why is that important? Well, if 3/4 of our atmosphere is nitrogen gas, it's kind of like the rule of thumb to look at. So anything that's a density less than 1.25 is going to float. All right, anything less than 1.25 is going to sink. So look at both of these are quite less than 1.25, so both of these will float. So they got rid of the hydrogen blimps and the hydrogen hot air balloons because of the dangerous conditions. It's flammable, that's probably bad. But what about this? This is not dangerous. It is not flammable, all right, and you're not going to blow it up. But what's the problem with having helium at STP? The question is, how do you make helium? We can easily make hydrogen gas with an acid and a metal, but how do you make helium? Well, you make it by radioactive decay is what you do. So, you have to find these caverns in the rocks or in the earth or someplace, and you can find helium. Helium is very difficult to come by naturally. So you have less helium, or the earlier scientists didn't have the helium at their disposal the way they did the hydrogen, okay? So anyway, last but not least at STP anyway, is carbon dioxide. So my question to you is, do you know what carbon dioxide will do in air? Does it sink or does it float? Well, let's find out. All right, why don't you go ahead and actually work this problem out, and when you're done, come back, all right? I'll be here. All right, how'd you do? Well, of course, I always put my equation there, and it's at STP, so I'm allowed to do this. And what is the molar mass of carbon dioxide? It is 44.01. I don't know if you remember that from how many times we did before. Divided by 22.4, and we get 1.96 grams per liter. So what would carbon dioxide do in air? Well, 1.96 is bigger than 1.25, so it's going to sink. Now, does that make sense? What happens when you blow up a balloon with your own, breath, all right? Does it sink or does it float? Well, it sinks. What's in our breath? Well, carbon dioxide is part of what's in our breath. We exhale the carbon dioxide. I'm not saying it's 100% carbon dioxide, but there's a lot more of it than oxygen gas, all right? So, it will sink. If you've ever seen, say, a fire extinguisher, all right, that's carbon dioxide. Where does it go when you push the handle? It goes down, doesn't it? All right. So that is more dense than air. That's right. Now look at number 4. This is the last one for the day, and it says, what is the density of neon at? Is it at STP? No, it's not. All right. It's at a different pressure and a different temperature. And so that is where we want to use this. Right here is what's going to tell us how to figure out the density. So let's go ahead and do that. Okay. All right, so once again, here is density is equal to mass per volume, but this time it is equal to, oops, I left off my equal sign. There we go. It's equal to pressure times molar mass divided by RT. Now, I went ahead and put everything in there. So I have my pressure, the 1.2 atmospheres. Notice it's in atmospheres, and I'm going to show you why we need that. Here's the molar mass of neon, 20.18. I found it in the periodic table. Here is my R, 0.0821 liter atmosphere per mole K. And what did I do here? I added 273 to 22. Now I want to show you what happens here. My atmospheres cancels, right? What else cancels? My moles gonna cancel, right? My kelvins are going to cancel when I do all that. And what am I left with? Here I have grams, and here I have liters. They're the only units left that didn't get canceled out. So if you didn't believe me before, maybe now you believe me that the units work out to be grams per liter, so it must be density, all right? So if you were to go ahead and do all this math, this is what I got. Now, I gave you, what, 6 sig figs. You don't need that many. Well, how many do we need? Well, right here is where 2 sig figs are. There's really infinite number of sig figs here because it's off of a chart. There's infinite number of sig figs here, and when I add 22 and 273, when you add, you take where that significant spot is in the ones, you put 3 sig figs. So I need 2 sig figs as my answer, and I got 1.0 grams per liter. So what will neon do, even in these conditions compared to regular air? It will float. Okay, well, that concludes our unit on gas laws. I hope this, some of what we said, this whole unit makes sense. It's something that you can, think about and observe, like when you think about, balloons floating or whatever, that I find this unit very, very much fun to teach. So I hope you enjoyed it too. So don't wait to be great. We'll see you next time. Bye-bye.